In this video, we're going to introduce the force of friction and how it is calculated, and then change our axes so that we are now no longer perfectly horizontal. We're at an angle. So we'll deal with forces on a ramp. Now, force of friction is something that you are probably familiar with. If you've ever rubbed your hands against each other or tried to drag something across a table, you've experienced friction. We're going to describe it as FF, which is basically a force that always opposes motion. It is the molecules that are in contact with each other as they are moving across. Now, force of friction, we're going to describe as the force opposing the motion between two objects that are in contact. This contact is required in order for friction to happen, and friction will always oppose that motion. So, knowing the direction of the motion or the attempted motion will help us identify the direction of friction. There are two types of friction. Static friction is essentially not moving. That's what static means in the world of science. So this is friction before something has started to slide. If you push on something, chances are you need to get it to start moving. Say you're moving heavy furniture. It is hard to get it to go. Imagine, if you will, that a surface feels very flat, but microscopically it's not. That surface has a bunch of different grooves on it, and then the object that you're trying to slide also has a bunch of different grooves on its surface. A good model that I like to use is imagine that you have your two fists that fit together, your knuckles kind of form those grooves. Friction is essentially you trying to slide your knuckles, your fists across each other. It's hard to do, especially if you are starting fully embedded like this, where they are um, nested in between the knuckles, the grooves that found their homes. But once you get it going, it can kind of ride along those grooves and the knuckles kind of bounce from knuckle to knuckle. That is dynamic friction or kinetic friction. Once you are in motion, it is a lot easier. That static friction is always larger than dynamic friction. Once you get going, if you can keep that motion, the grooves don't find their homes. But as soon as it stops, it settles in, and then you have to overcome static friction again to get it moving. Now, if you were to graph this, it looks something like this, that if you were to push a box, it's going to require more and more force just to get it to start. It'll keep pushing back on you until you finally get it to move. Once it starts sliding, that force actually drops. That maximum static friction is no longer required. And the force of friction, it is going to maintain basically at some constant that is lower than the static friction is. We can calculate the value of both dynamic and static friction. It's the same relationship. The force of friction, FF, is equal to this coefficient. It's the Greek letter mu times Fn. We've seen Fn before. That's the normal force. It's the force that the surface is pushing back. And it kind of makes sense that it shows up in here. How you can think of it in this knuckle analogy is if I were to push my hands together with more force, the surface is pushing back with more force. Now, that means that the grooves are basically being pushed together, so they are harder to slide across. So, normal force, how hard the surface is pushing back, increases friction. The other thing that increases friction is this Greek letter mu. That stands for the coefficient of friction. This is a unitless value. If you think of the units here, you've got force of friction, that's in newtons, is equal to something times newtons again. That something has to have no unit at all, or our units would not line up with our force on both sides. Now, there are a lot of different coefficients of friction. It depends on the surfaces and how they interact with each other. So you'll see like steel on ice has a fairly low coefficient of friction, pretty close to zero. Whereas something that is grippier, like steel on steel when it's dry or climbing boots on rock, that friction increases. Static friction is always higher than dynamic friction. So think of the larger the mu value, larger coefficients, our surfaces are kind of quote unquote sticky. They grip better, and a small coefficient of friction are surfaces that are relatively slippery. This value will either be given to you, it'll be a known from those surfaces, or it's something that you have to calculate knowing FF and FN. Static friction has a special feature to it that it does not always have to be the same thing. And if you think about it, that kind of makes sense. Basically, if I push on a really heavy box and it doesn't budge, that doesn't mean that's the maximum amount that static friction could be. I could push harder and then it pushes back the same amount. Or I push harder still. It still gives me equilibrium. The box is not moving. Static friction was any of those forces, basically anything up until the maximum force that static friction can hold. Once you hit that limit, though, it's no longer static friction and onto dynamic. So when you calculate static friction, it's basically calculating the limit of what static friction can be, but it's going to be equal and opposite to whatever that external force is. Because of that, when you see this in the data booklet, you're going to see force of friction written twice. The static friction is equal to or less than, and then dynamic friction is always equal. There isn't that range. The way we're going to look at it most of the time is we're just going to use this general form and say FF is equal to mu times Fn, the coefficient of friction, times the normal force. We can calculate that by looking at some of these forces that we've seen before. F is some external force. It could be a push or a pull. There generally is something. If not, it's those other forces that are acting together. Fg, always going down towards the center of the Earth. We know how to calculate that. That's mass times gravity. Remember that gravity is 9.8 newtons per kilogram. Fn is the surface that is pushing back perpendicular to itself. Now, this is a situation where Fg and Fn are perfectly opposite each other. If that object is in equilibrium, they should equal. They should cancel each other out. Now, this is only true if the surface is perfectly flat, so that the perpendicular to that surface is opposite FG, or if we have a scenario that we have like a string that we're supporting that block a little bit, we might not see these equal there as well. But in a simple situation, those are often found equal to each other. And then FF is this force of friction that's opposing the motion, opposing that external force in this case, and we can calculate that using our new equation, mu times Fn. What's great about this is these are simple equations that are going to interact with each other to solve for something a little bit larger. Let's see an example. Santa's sleigh is loaded up with toys for all the good little girls and boys until it has a total mass of 2,000 kilograms. What is the static friction force that must be overcome if mu s, the static coefficient of friction, is 0.1? Well, let's look at our diagram. Fg is down. That sleigh has mass. It has a force of gravity, weight. We can calculate that. Fg is equal to mass times gravity. 2,000 times 9.8 is 19,600 newtons. We know that sleigh is being supported. It is in equilibrium until it's not, basically. It's in equilibrium until that static friction has been overcome. So assuming equilibrium, Fn, that snow surface pushing back up, is also going to equal Fg, which is 19,600. Now, the force of friction is related to Fn. We calculate zero point 0.1 times Fn to get a force of friction of 1,960 newtons. That is the force that friction is able to supply. If you push with less, friction will push back with less. If you push over that 1,960, it will start to move and the friction will change anyway. So that is the limit they are trying to exceed in order to get the sleigh to start moving. Another common example that you might see is finding mu, the coefficient of friction of a shoe. A really easy experiment to do with this is if you have a force probe and you pull with a force probe at a constant velocity. Constant velocity, as weird as it feels, is still equilibrium. That's still not speeding up or slowing down. It's maintaining its first law of motion. There is no unbalanced force because there is a force of friction that's canceling it out. So assuming we have a force of pull of 1.92 newtons, and the force of gravity, the weight of my shoe is 2.77 newtons. We can look at some relationships. We can say, oh, force of friction must be equal and opposite to the force of the pull in order to maintain that constant motion. It is in equilibrium. So FF must be equal to 1.92 as well. Fg has to be canceled out by the surface of the table or the floor, whatever you're dragging this on. Fn has to equal Fg, which is 2.77 newtons. Okay, why is that helpful to find all of these forces? Well, if I want to find mu, the only way I can do that is to calculate it or have it given to me. Here, the calculation, the equation that includes mu, is the force of friction equation. Force of friction is equal to mu times Fn. I now know what Ff is, and I know what Fn is. I can plug those in to solve for mu to be 0.69. Typically, mu, coefficient of friction, is going to be between 0 and 1. It's not impossible to be above 1, but if it is, You'll notice something interesting about that surface. It's kind of a tacky feel. It's something that's really, really grippy in order to get something that's one or above. All right, now let's put all of these forces on an incline and see what changes if you have forces on a ramp no longer perfectly horizontal. Well, let's say I have this object that is sitting on a ramp. There's still a force of gravity. Gravity doesn't care that there's a ramp. It goes down to the center of the earth, straight down, no matter what the angle of incline is. But what does change is now my normal force being perpendicular to the surface is no longer equal and opposite to FG. It is now pointing in a different direction. It's pointing at the slope perpendicular to the surface. Also, remember FF, the force of friction, is the force that is resisting motion or opposing that motion. If I were to let this go without friction, it would slide down. So typically, the force of friction is supporting upward. Now, that's not always the case. If you pull something up a ramp, force of friction might be pointing down. But in this case, we'll just say with all else being equal, force of friction is pointing up this ramp. Now, this is really hard to deal with because things aren't equal or opposite. Not easy to see canceling out. So if we can somehow turn this picture into this picture, it's going to be a lot easier for us to find a net force of zero and figure out how everything is connected together. So let's do that. You'll notice the only thing that's different about this picture and this picture is FG. We're going to try to make FG opposite of F and Fn and figure out those components. Now, this is different than when we saw the components being X and Y. We were looking at just horizontal and just vertical. Here we're going to tilt that and now be at an angle. So we have basically break FG down into these components. And we're going to call it parallel and perpendicular to the ramp. So FG is pushing down the ramp a little bit. It's not perfectly into the ramp. Some of it's trying to make it slide down. So we can figure out how much of it is in that component, and we can figure out how much of FG is in the component that's perfectly perpendicular to the ramp or normal to the ramp. This makes a triangle if we do it in the right way, and that triangle looks something like this. By definition, the parallel and perpendicular are going to be at right angles to each other, and the angle of our ramp ends up being a similar triangle to the triangle of forces that we just drew. That angle, theta, shows up here between FG and F perpendicular. Now, what's weird about this right triangle that's different than we normally see is this right triangle, the hypotenuse here is FG. It's the one that's perfectly vertical. We're used to seeing the hypotenuse at a slant. Here, FG, the hypotenuse, is vertical, and that right angle is kind of at a slant. So we can use some trigonometry to solve for this. If I find the sine of theta that's opposite over hypotenuse, the parallel force divided by the force of gravity, and I can rearrange and solve for the parallel force as FG times the sine of theta. Do the same thing for cosine, and we find that it's the adjacent side, F perpendicular over FG, or solve for F perpendicular, and that's force of gravity times the cosine of theta. So let's do this. Let's plug it in. Normal force, Fn, is the force perpendicular to the surface. Well, let's look to see how that's going to fit. If we are looking instead of Fg at this parallel force and perpendicular force, now normal force has its opposite. Its opposite is the perpendicular force. So normal can be set equal to the perpendicular force. They are canceling each other out, especially if we're in equilibrium. Even if we're not, it's rare that we see a situation where an object is accelerating up off of the ramp or into the ramp. Typically, Fn and F perpendicular will cancel each other out. The friction force, in this case, is up the ramp. If this object is in equilibrium, these forces are equal to each other. We know it's true that FF is always equal to mu times R, but if it's in equilibrium, we also know it's true that these are going to be equal to each other, the parallel force and the force of friction. All right, let's look at all of this together and solve one giant problem. Before we do, a quick meme to remember that this is challenging to solve. This is easy to solve. So if we can turn this FG that's vertical into a parallel and perpendicular component, we're going to have a much easier time. Again, it's not the only way. Like technically, you could find the components vertical and horizontal of Fn and Ff and solve for that way. But it's going to be a whole lot easier if we can find a perpendicular and parallel component. All right, let's put all of this together and solve for our first official ramp example where all the forces are acting on this ramp. Now, we have a situation here we're going to assume is equilibrium, where there's an object with a mass of 10 kilograms sitting on this incline of 40 degrees. I want to calculate what the coefficient of friction is going to be between that object and the ramp. First, we can solve for Fg. If I know the mass, Fg is just mass times gravity. 10 times 9.8 is 98 degrees. That Fg is perfectly straight down. It is doesn't care where the ramp is. But because it's going straight down, part of that is parallel and part is perpendicular. I can take that parallel and perpendicular and create a triangle by sliding that angled down, that parallel force down. And the angle between the perpendicular and FG is 40 degrees to match the angle of my ramp. Now, F perpendicular is the one that is attached to that angle. It's adjacent. So we're going to use cosine. F perpendicular is FG times the cosine of theta. That is 98 times cosine of 40 is equal to 75.1. Plug that in. I can do the same thing, only using sine to find the parallel force. Parallel force is Fg times the sine of theta, sine of 40 degrees. That gives me 63 newtons. Now, I have put both of those on a separate free body diagram where I have ignored Fg entirely. Now, because of this, it's easier for me to see where Fn is going to show up. Fn is just opposite of perpendicular. So if F perpendicular was 75.1, so is Fn. That's also going to be 75.1 going in that direction. And that makes sense. This object is not accelerating up off of the ramp or into the ramp. Uh, that needs to be in equilibrium, at least in that direction. In this case, this object is also in equilibrium in the parallel direction, which means FF going opposite the parallel force should also be 63.0. And because of that, I know I can use this equation. I know what FF is, 63.0. I know what the normal force is, 75.1. I can plug those in and solve for mu. Mu in this case, remember, usually between 0 and 1 is 0.839. Again, it's a unitless number, but we can see how all of these different parts of this equation all kind of boil down to us being able to use that final equation because we know what FF and F perpendicular are. All right, so takeaways in this lesson, you should be able to understand force of friction, how it's related to the normal force and coefficient, and then quantitatively compare these surfaces using that coefficient. Um, Also, you should know how this incline is going to impact things like the normal force and be able to calculate parallel and perpendicular forces of Fg uh, from whatever angle that ramp happens to be. And then with all of that, be able to work backward and figure out what the force of friction has to be in order to maintain this equilibrium on a ramp.